Hey guys, I thought that today would be as good as any to try and introduce transformers to everybody. This is not necessarily a new topic. The specific one that we're going to use came out in, I think, 2017, 2018 with the Attention is All You Need paper from Google. However, there's a lot of people that still don't understand necessarily how they work or why they work. And so I wanted to give everybody a rundown on how to train a language model and then how to use that language model. So this first little bit, we have a data set already here, and I want to give credit where credit is due. A lot of this is going to come, especially this project idea, comes from a book called, it's from Dennis Rothman, called Natural Language Processing with Transformers. It came out in 2020. That's where I'm getting this data set and the general idea of how to train this. We're going to be using the Hugging Face transformers, tokenizers, and data sets. So first, let's talk about the data set. This is from Project Gutenberg, which is an open source library of books that you can download anything you want from. We are going to download this or I already have it, but I'm going to give you a command that you can use. This is an IPYNB, a Jupyter notebook. Visual Studio Code has an excellent extension on interpreting these and running them just in Visual Studio Code. You don't even need to open up a browser. But in order to run commands like curl, you have to put an exclamation point at the beginning of it. In any case, we're just going to copy this link. Basically, yeah, this is the book, Transformers for Natural Language Processing, that we're getting this data set from. It's from chapter 3. I highly recommend, if you're interested in this stuff, go read the book, and then we're outputting it as cant.txt. We are not going to run this because I already have it, but that's there just for you guys. On to the second part. Install transformers, tokenizers, and we are going to install data sets. We don't need this comma. This is another one that I'm not going to do because I already have it installed, but this is how you get pretty much everything that you need for the actually no, it's everything that you need for this. So we're going to start with let's do this. Train a custom tokenizer. I'm going to avoid saying from scratch because we're going to be importing a tokenizer, but we are essentially going to be training this from scratch. We're using a byte level BPE tokenizer, which it looks at subword tokens. Essentially, so we have, let's look at tokenizers real quick. Word level. We are with word level tokenizers. If I have a sentence like I am going to the store, this would be the same as running a dot split on it, or at least almost the same, and you would get an output that looks a lot like I am going to the store, except this would be lowercase. If we go to character level and we take this exact same thing, we're then going to get an output of this, except you can see where I'm going with this. We're doing character by character. And I hope that you guys can see the weaknesses of both word level and subword level. But just in case you don't, let's go over the happy medium that is subword. Where we would get something really similar for a sentence just like this, except we're going to be splitting this. We would have both go and ing, and that ing would end up being word final like this. The reason that we care about these is if we split just on word, we end up losing a lot of information. Like, let's say we have nationalism as a word, right? There are we have nation, we have nation, we have ul, and we have ism. And all three of these are important as far as our semantics. You can get by using word level tokenization for certain specific projects, but when we're building a language model, we want to capture as much information as possible. And while this isn't capturing all of the information that's possible as far as going character level, it's capturing most of it. There is a weakness to character level encoding though too, where you end up encoding meaning to the letter G and the letter E. So eat, eternal, and erroneous all end up having this E in them, and the model ends up tying a little bit of similarity to those words, even though they have nothing in common other than the way that they're spelled. The linguistic way of describing this is that our orthography is very arbitrary, so going character level ends up losing more information by giving too much. So subword is one of the best ways to do this, and we're specifically doing a byte level subword, so we're not even looking at this English orthography, we're looking at the bytes in memory, the actual hexadecimal that is used to represent this character, to make it just a little bit even further accurate for the computer. But how we're going to do that, from pathlib import path, so that we can show the tokenizer where a thing is, and then from tokenizers import byte level BPE tokenizer, right? And so our paths are going to equal, and we're going to do a list comprehension here, string, just in case there's an integer or float or something, of x for x in path. And this is a really easy path for us because Kant AI text, or Kant text, is in the same folder as us, but this is where you would put the path to that data set wherever it is. .glob, and then this is going to look a little weird, but .txt. It allows it to split things up for us. And then, so here's where we're actually going to initialize. Tokenizer equals byte level BPE tokenizer, da-doom. And we don't need to add any arguments here. And then we're going to train it. Paths, vocab, size. And I just want to explain the reason why we're doing this list is so that we could train as many things as we want. Like if you want to add to this text, if you want to go on Project Gutenberg and download all of Edgar Allan Poe's stuff or all of Shakespeare's stuff, you can add to this. This is meant to be added to, and I hope that you do. I hope that you extend this. This is a vocabulary size that I determined before through some testing, but what you should do is you should look at all three of these arguments that I'm about to give you, the minimum frequency and the special tokens. So, vocab size. This is going to determine the size of our tokenizer, and if it fills up this entire vocab, it's going to stop. So you need to find a number for your language model that you want to build that actually encapsulates the majority of your meaning in order to get a really good distribution of all of your tokens. If you don't have that, you will never get good accuracy. So this is probably the most important part of training any NLP model, is coming up with a tokenizer and really tuning that tokenizer to make sure that it is giving the model correct information. I've gone over this on my channel before, but the reason for that is all of the text that we are going to get from this Kant text, and I'm going to show you this as soon as it's trained, all of this needs to be converted into numbers because our model can only handle numerical input. All machine learning models can only handle numerical input. And tokenizers are what we use to change that text into numerical input for the model. Our minimum frequency. This determines the number of times that a token has to appear in the data set in order for it to go into our vocabulary. If we put this down to 1, it just means that every single word is going to go immediately into the vocabulary based on where it is in the data set. 2 means it has to appear twice. 3 means it has to appear thrice, so on and so forth. The reason why we don't just immediately do 1 is we want to get a general sense of the words that are used. We don't want to get really random words like erroneous that may only appear once in the data set. Or we don't want to get too bogged down in jargon for our general language model. If you're training something a lot more specific, you may consider going down to 1. Or if you're training on Reddit posts, for example, you may want to go up to 3, 4, or maybe even 5, just to make sure that you're capturing the way that normal people are talking in that data set. In this case, because we only have one author, it's okay to do 2, but I encourage you to experiment around and find something that you care about for this. So the special tokens that we're adding, we want a start of sentence token. We want a pad token. We want an end of sentence token. We want an unknown token. We want a mask token. And we're just going to add these tokens straight into our data set right in the beginning. And here, I'll let this run while I talk about it. These tokens are all pointers for our model that are going to take up the 0, 1, 2, 3, and 4 slots in our vocabulary. We're going to be doing masked language modeling. The way that masked language modeling works, I'm going to Google this real quick so that we can look at an image. So here's an image for it. We have our transformer encoder, which we can look at as the first portion of our transformer model that takes all of these tokens in the numerical form. And the way we're going to do it is we'll take our sentence, we're going to tokenize it, and during that tokenization process, we're going to add a mask to one of these tokens. And as part of the training, we task the model with guessing what's behind the mask and seeing how well it does. Here's BERT, because we're going to be using BERT, right? We have our beginning of sentence, and then it'll mask something, transfer it to the model, and then it will see how well it does guessing. And in this case, that softmax, all of these percentages will add up to 1. The top 10% was improvisation, and we can see that that's the right one in this example. That's what we're doing. That's why we want the mask token. So let's now use our data set. Let's use our tokenizer. We're going to create a folder here. Right, and then just in case you don't want to actually have to do that, we'll give you this command to just create the folder. But we'll just do token here instead of this. This will allow us to save our newly trained tokenizer. And this is the way that it ends up looking we have our vocab, and it's saved as a JSON file. You'll notice there's a lot of interesting tokens that you see in here. Most of them have this little G at the front. In fact, if we just highlight it, you'll see how many of them there are. Some of them are only these G's. Don't worry about that. Those are bytes that, and it tends to simplify it for itself to take up less space and to be faster. This only helps us, but you can see how long the vocabulary is. It's 52,000 tokens. In fact, actually, ours only goes up to 19,000. So if we wanted to really optimize this and make sure that we're using our space effectively, we could change this down to 20,000. And when we save it, it ends up, for some reason, it looks like using more than it did before with the 52,000. Let's say 25,000 and see what that does. This is what I mean, though, by experiment around with it and see what happens. You know, what's good for your model. Now it's 22,000. So with the 52,000, what did that do for us? Oh, it didn't change because I had it open, so it couldn't save it. All right, let's take a look. Yeah, it looks like there's about 23,000 tokens that end up being in our model in that vocab. That's fine. And then the merges. This, I'm not going to go into everything about this, but basically this allows the model to keep track of common things that appear close together. Uber, right? What this does is it gives the model an idea of how to reconstruct certain words that maybe don't appear all that much. Boasting, frequently, foolish, friendship. That's basically it, though. You don't need to give that a lot of other thought unless you really want to get into tokenizers, which is one of my favorite subjects. So, next part. What we're going to do is load this tokenizer. This is something that I got really frustrated with when I was learning about AI, is they would always tell me how to save stuff, but they would never tell me how to load stuff, and it was rarely intuitive. It's gotten a lot more intuitive since then. So, implementations, import byte level BPE tokenizer from tokenizer dot processors. Whoops. Import BERT processing. And here's where we get introduced into the actual model that we will be using. This is the reason why we added these. We want to be able to use it with BERT. A lot of tutorials will have you do auto tokenizer from tokenizers. That's fine. Auto tokenizer, this is what that looks like. And I think it's just from transformers. You import auto tokenizer from transformers. Import auto tokenizer. Yeah. So what this does is it allows you to automatically grab whatever tokenizer is used for a model. This is a really easy way to get exactly the tokenizer that matches. I would encourage you to research tokenizers a little bit more so you know what needs to appear within the tokenizer for it to then be processed by a particular model. I can guarantee if you have a better tokenizer than another person or than another company, it doesn't matter which model they're using, your model is going to outperform them. And we're going to grab both of those files, vocab.json and merges.txt. So now our tokenizer is our loaded model that we trained right here. Now if we call tokenizer, we can immediately use it. So let's see. So if we run this, we see exactly how it's splitting things up. And you'll notice immediately it's splitting the L and anguage. This is not how we normally think of these words splitting when we, like for grammarians in English. That's fine. Or look at TR, ands, form, ers, right? This isn't how we normally think of it, but that doesn't mean that it's wrong, and this is actually going to work out in our favor with the real model. And if we run the same thing but without tokens, we get to see the number of tokens and the attributes of those tokens, which are input IDs, type IDs, tokens, offsets, attention mask, which we're going to go into in a bit, special tokens mask, which these are the special tokens, and overflowing. But let's move on so that we can get through all of this. BERT processing, we're actually going to call it. And we want to tell BERT what to do with each of those special tokens. Specifically the start and end tokens. So this is the end token. Token to ID. And you'll notice that these look really similar. It's because they are. We just want to make sure that BERT knows that this is the same as this. And we're going to do the same thing with the start of sentence token. And then tokenizer.enable truncation. We want to be able to truncate each input, everything that goes into the model, so that it hits our max length and doesn't go any further. The reason for that is we don't want to overload memory. And if you get really good at pre-processing, nothing over your max length is going to go into the model anyway. So now that we're going to get into the actual model training, we want to check our GPU. If you don't have a GPU, you can run this exact thing on Google Colab or on AWS or on Kaggle. I recommend you get familiar with any of these if you don't have a GPU, because it'll be the best way for you to break into the field. I do have a GPU, and we can look at it using the NVIDIA SMI command. This is where we can see, this is the GPU that I have. This is how much memory it has. It's an NVIDIA GeForce 3080. You don't need 10 gigabytes of data on your GPU to train this model, but that's what I have. If you have more than that, you will definitely be able to do this. If you have, I think about 5 gigs is enough for this, so you could do this with a 2060. You may even be able to do this with a 1650, which I haven't tested that, but I think you should be able to. This is how we get our computer to actually talk to our GPU when we're doing machine learning. You can do this with TensorFlow as well. I'm very partial to PyTorch, so we're going to use PyTorch. And we get this true. CUDA meaning our GPU, right? You can see this here. I'm using CUDA version 11.7. So if we actually, let me show you how to get this. So installing PyTorch is a little bit different than just doing a pip install, but you can, installing the latest stable one, you just pick your operating system, you pick how you're going to install it if you want to do Torch, and then you pick which CUDA level you have. This is the highest that is currently supported, and if you don't have a GPU, You can run all of this on CPU. Don't fret. This just makes it go faster because you're able to do parallel computing. But you can do all of this on a CPU if you don't have a GPU. I would recommend, just because it goes a lot faster, that you go to collab.research.google.com and connect and kind of get into this on your own. You would want to do a new notebook. Oh, I've got to allow pop-ups. But once you sign in, you'll see something very similar to this, and you can just get going. You can write exactly the code that you see here. So we're going to use BERT. Actually, you know what? Let's use RoBERTA. RoBERTA is a slightly larger version of BERT. Let's look at an image so that we can explain this real quick. You can see here, these are different tests that exist in NLP. Squad is the question answer data set, right? And this is our accuracy that we're getting. I would assume this is precision and then this is recall. For this, RoBERTA allows you to get higher accuracy because it has more parameters and the model's set up slightly differently to BERT. This is the large version of BERT, and it gets about 90. So you can see there's about a 4% accuracy difference, or a 4% precision difference, and about an 8% recall difference. It's not that huge, but we're gonna do this because I think it'll be fun. Basically, we're just gonna set up what type of RoBERTA we want to download so that it automatically configures itself the way that we need it. We're gonna set the vocab size to be the same as our tokenizer. That way we don't have any weird non-overlap. No, we need 514. And the reason for that is we set our max length up here to be 512, but we're going to add a start and an end token to every single thing that goes through it. So we want 514 because it's 2 higher than 512. Make sure that this is whatever your max length is plus 2. In fact, if you want to set your max length to a variable, a global variable, and then just put in here max len plus 2, that works. The number of attention heads. We're going to do 12. This is just coming from the original BERT paper. 6, also coming from the original BERT paper. And we're just going to set our vocab size type to 1. Easy. So now we can print this and go through exactly what is made up in RoBERTA. You'll see here our activation function is a GELU. That may be something different than what you're familiar with if you're into sigmoid or ReLU. Maybe you're a little older and you're into TANH or something. This is what we're using. You can change this. If you put in hidden activation or hidden ACT, you can use any activation function that you want. All of these are things that you can initialize and change. But you'll notice the ones that we did change are exactly what's in our config. That's what we want it to be. This is one of the most important parts of this, because if at any point you want to change any of these things, you can reinitialize your model with a new config. You'll receive a warning and everything, but if you train it again with the new config, it will then adapt to the new version of things. It's really handy. This is just a nice way to make sure that you're using the same model and that model is 100% customizable every time. So let's keep going. From transformers import RoBERTA tokenizer. And we're gonna do the fast one. No, so the fast tokenizers are written in Rust and their config is a teensy bit different, and I don't want to risk running into an error while I'm doing this. We just pass in the folder. It knows what to do with the vocab and the merges. And then we want this to be 2 less than whatever we initialized this at, so 512. We'll do the same one as earlier. But this is how we change this byte level BPE tokenizer that we trained and we loaded and everything. This is how we change it into a RoBERTA tokenizer. So this is essentially the same, like you could use auto tokenizer here instead of RoBERTA tokenizer. This will just change the config. It'll add a config to this that allows it to work for our use case. And then we're going to do RoBERTA for masked language modeling, and we're going to immediately create a model too. And we're going to initialize it using our config. And then we'll print it so you can see what the model actually looks like under the hood. This will take a sec usually because it has to download these. I already have this downloaded on my computer, so I didn't have to do that again. But we see our first layer in the RoBERTA model is embeddings. This is probably the most important layer and the layer that has the most chance for improvement in the future, because this is the actual numerical representation of each of our words. Our word embeddings here, it's pretty cool. There's 768 dimensions, meaning that each word in that vocabulary is getting 768 dimensional features given to it. They're positional embeddings, which is the max length also multiplied by 768 dimensions, and the token type. So we're essentially looking at the word. This is supposed to be a semantic embedding, but it's difficult to call it that considering, like, if you've actually studied semantics. The positional embedding just looks at where it actually appears in the sentence. This helps for it's pretty much all languages that require specific positions for words. Like English is really heavy. When you get into languages that are more flexible with their word order, like Slavic languages, Chinese comes to mind as well, Japanese comes to mind. The ones that are more flexible, this ends up being a little bit more difficult and erroneous for the model, but I wouldn't take it out. We just need to figure out a better way of doing this embedding. And then token type, where you're looking at either part of speech or whatever types that model has encoded into its embeddings. This is the next layer is the encoder. With transformers, let's take a look at that real quick. If we look at this, oh, it's not going to let me zoom in all the way. Anyway, this is what a transformer looks like under the hood. You have your encoder over here, that's this block, and you have your decoder over here, that's this block. BERT and RoBERTA, all of the BERT-like models, if we, in fact, Google this, BERT language model, bidirectional encoder representations from transformers. They literally trimmed this off of it and made an encoder-only model. I'll explain really as simply as I can the intuition behind this. If we take our inputs, so our sentences from this Kant text, I'm actually going to use translation as an example because this is I don't want to use an encoder only model for the whole transformer. If we take a sentence in English, like my name is Chris, and then we take a sentence in French that we want that to be translated into, je m'appelle Chris. right? If we take both of these and perform the exact same encoding on them, this then goes through its embedding layer and goes through attention. It goes through a neural network to transform that encoding into an embedding that looks, or it transformed that embedding into an encoding that is a lot more useful to the model, or is supposed to be more useful to the model. We then do the opposite thing with the output, where we encode it in the exact same way, but then we try to decode that model, that encoding or that embedding, to look similarly to whatever gets encoded on the input side of things. We then have this portion of the model, which is where the magic happens, where we end up comparing the two vectors and seeing what's actually different between them and building relationships between each part of those encodings. That's why it's called an encoder and a decoder. We're doing encoder only model today. I'm going to do a decoder only model next time, and then I'll do a full encoder decoder transformer after that. Once we've compared them and tried to build an underlying relationship between them, we go through essentially a classification process and a softmax to help us normalize the output into into what are supposed to be probabilities that add up to 1, and then we output those probabilities. And we have, from this output, we can then take whatever is the most, or maybe the top 3, top 5, whatever we would like. There are really cool things that happen under the hood in all of this as well. This scaled dot product attention. If you know about dot products in matrix multiplication, you know that they can get out of hand pretty easily, especially when you're multiplying a lot of these matrices. And as we went over, each of these matrices is 768 dimensions. So this has the potential to go out of control really fast, so we scale it. And there's just a lot of really cool stuff going on under the hood with transformers. I encourage you to study them. They're really, really cool. For our model, something you may be interested in is looking at the number of parameters. We talk about GPT-2, GPT-3 having upwards of 1 billion parameters and how big they are. Oh, shoot. I need to actually do the function. Our model ends up having, let's see, let's count this. 1, 2, 3, 4, 5, 6, 83 million parameters. So it's a quote-unquote small language model, but it's actually pretty substantial. It's nowhere near the size of GPT-3, but you could make it that big by changing these. You know, you want to change your positional embeddings, change your vocab size to be a lot bigger, change your attention heads, change the hidden layers, and you can then get this to be as big as GPT-3. I'm giving you the ability to train something like that. GPT models are decoder-only models, so you would want to tune in next time and look at those to actually train something similar to that. But this would be, for the record, encoder models are really good for tasks like classification or question answering, something where you need a specific answer out on the other side. Decoder models are much better at things like language generation or story generation. They're much worse at the classification sort of deal. And encoder decoder models are much better at sequence to sequence problems, things like translation or summarization or named entity recognition, things where you are classifying your input, but you're building on top of it, you're generating extra stuff on top of it. And that's an easy way to look at this, at kind of a simplified version of the transformers. Encoders are for classifying, decoders are for generation, and using both allows you to generate on top of your classification. We're not gonna dive really deep into our parameters. I hope that doesn't get on anybody's nerves, but you can on your own, and I think that you should. This video is just getting long already. So let's build our data set, and then let's train our model, and then let's test it a little bit. So from datasets, import load dataset. Dataset equals load. Oh gosh. I saw it for a second and then it disappeared. I hate when VS Code does that. This is going to be a text data set. We can tell that by it being txt. And then we need to give it the actual data files. Data files equal Kant.txt. And then we're going to just test, make sure that this actually gets loaded. When you make these dataset objects, they automatically create a train category that you have to index into. It's really annoying if you forget that, so just don't forget that. In fact, we're going to print the dataset first so that you can see this. This is the actual dataset. So it downloaded and prepared the dataset. This is how people download datasets from Hugging Face, the hub. This is the actual dataset itself, where it's a dataset dictionary. It uses arrow pointers to kind of create a cache version of your dataset. Makes it really fast and nice. This is how many rows happened, and you can see immediately the first key in the dictionary is train. So we always have to remember to index into train when we're doing things. Here are the first 11 tokens, or I guess 11 lines in our data set. It looks like it's grabbing new lines, or I guess empty lines a lot. That's too bad. Hopefully that doesn't change anything, but we could use dataset processing to get rid of all of these empty things. I'm not going to do that right now, but when you're training this yourself, you should. You can find that just here. Here. This is where you can do things like sorting, shuffling, filtering, and this is where this is what you would use as the filter, right? Dataset.filter, and you would write a little lambda function to get rid of all the empty ones. We're not going to do that right now though. So from transformer, if you want to optimize this, you know, put all your imports way up at the top. Import data collator. This is just a collator that will essentially line up all of our inputs from our data set into something that our model can use. And we're going to instantiate it real quick. Equals data collator for language modeling. We have to give it our tokenizer. It's going to ask whether we're doing masked language modeling, which we are, and then we want to give it a probability. I would encourage you to experiment around with this. We're going to do a 15% probability that something will be masked. You can go, I wouldn't recommend going higher than 50%, but you can. Generally, I wouldn't recommend going higher than 30%, but we're just going to do 15% for our purposes. And then we're going to use the Transformers API for trainer and training arguments. This will make it really easy to, like, we don't have to write all of the custom functions ourselves. Training arguments, trainer. So training args equal training arguments. And what sort of arguments do we want? Output directory equals we need commas. Overwrite output directory equals we don't need this. Number of training epochs, we're going to do 3 per, and this is a newer API for this, per device train batch size. We're going to do 64 because I know that my GPU can handle that. If you're running into memory issues, this is the first place you come. You know, put it down. Normally we want these in powers of 2 because parallel computing works best in powers of 2. So your next one down would be 32, and then 16, and then 8, then 4, then 2. If you're running into memory issues, change this down. If it still doesn't work, I mean, there are other things you can do, but that's the first place you go. Save total limit equals 2. Da-da, and then let's write our trainer. Model equals model. This is our RoBERTA model. Args equal training args. Let's scroll down so I can actually see this. Data collator equals data collator. This is why I'm naming things the way that I am. And train dataset equals dataset train. If you want to run a train test split for something more like classification instead of a language model like this, you can do that. And you would do that by doing like dataset equals dataset dot train test split, and then you'd say test size, and you'd specify this as a percentage, so 0.1 would be 10%. And then if you do that, oh shoot, so you'd need to actually cast it. You'd need to, up where we're doing this, import dataset as well, and then cast it using that dataset, and then do this. Unfortunately, I don't think, oh no, that did work. I guess you just index into the actual dataset instead of the dataset dictionary, and then you can, then it adds this test, and it just subtracts 10% from the final number. So you'll notice this ends up being really close to the number of rows. Yeah, it's just 10% of the number of rows of our data set that we loaded before. This is what you would do if you actually want to evaluate during your training. I'm not going to do that. I don't remember if this is in training arguments or report to, no, it's in training arguments, and you'll do none. You don't want it to be the actual object. Let's take a look at this. Print dataset dot features. So it's text. We may want to tokenize all of this. So def tokenize batch, and we're going to do this. So return tokenizer batch true, truncation equals true, max length equals 512. And then we're going to do dataset equals dataset.map tokenize patched equals true. So we can, I guess there are non-strings in here. I'm not sure where those are coming from. Name text, expected length 512, lookup length 1000. Let's get rid of this. That'll work. But as soon as this all it does, and I'm gonna add a little piece of code here to actually print it. So that we can then see. This should add input IDs and attention masks to everything to actually give our model the things that it's looking for, because right now it's saying the following columns in the training set don't have a corresponding argument in RoBERTA from asked.lm.forward and have been ignored. Text, right? it's not going to just take the text. So now we have input IDs, we have attention mask. What this does, and if we print data set train, just print the first, or I guess this one, you can see what that looks like, where the input IDs are just the tokenized version of the text, and the attention mask is the mask of attention for the input IDs. So this should help us out when we're actually training. Oh yeah, there we go. So text was ignored, but it's grabbing the input IDs and it's grabbing the attention mask, and it's doing the exact same thing. This is what I was talking about earlier with the fact that our models cannot take text. In fact, they refuse to take text. They will only take actual numerical IDs. And this is new, that it wouldn't tokenize during the data collation, like it probably should. You know, we specified the collator. Now the collator is making sure that these input IDs are lined up the correct way. And I'm gonna edit this out, but we'll wait for it to train, and I'll come back after the training. So now that that model has been trained, you can then load it similarly to how we loaded the tokenizer before, where you just do from pre-trained, you grab RoBERTA for masked LM from pre-trained, and then specify our Kant AI BERT folder where we have in our runs, I guess. Oh, I forgot. Save model. And then we're gonna save it in Kant AI BERT. Boop. And there we go. Now we have our config.json, we have our PyTorch model.bin, and our training args binary file as well. But that is everything on this one. Thanks so much for watching, and come back for the next one.